In the Black-Scholes world we built in episode 10, the interest rate R was just one constant number, a single value that never changed. But step outside that idealized world, and you discover something remarkable. Interest rates are not just one number, they are an entire curve. Each point on this curve tells you the annualized yield for a bond that matures at that horizon. Short-term bonds on the left, long-term bonds on the right, and the shape of this curve changes constantly. Let us watch it evolve through one of the most dramatic periods in modern financial history. By mid-2019, the curve briefly inverts, short-term rates exceed long-term rates. Then COVID hits, rates collapse, the curve steepens sharply. Through 2021, it stays steep with near zero short rates. The Federal Reserve begins hiking in March 2022, and by July 2022, the curve inverts again deeply. By mid-2023, it reaches its deepest inversion in over 40 years. Finally, in late 2024, the curve uninverts, returning to a more normal shape. Now, this inversion is not just a shape. Every sustained yield curve inversion since 1955 has preceded a U.S. recession. The 2022 inversion lasted roughly 26 months, the longest in modern history. Its track record remains, as of now, anomalous. So here's the question this episode will answer. What mathematical process generates this curve? We will build 4 answers, each more powerful than the last. Vasicek, CIR, Nelson-Siegel, and finally the Heath-Jarrell-Morton framework, where specifying the volatility alone forces the entire drift, and one equation governs the evolution of every rate at every maturity for all time. To understand yield curves, we start with the simplest possible bond. A zero-coupon bond pays exactly $1 at maturity T, no coupons along the way. Its price today, P of TT, is the risk-neutral expected value of the discounted payoff. If you have seen episode 12, this is the fundamental theorem of asset pricing at work. From the price, we extract the yield, Y of T, T. This is the constant rate that, if applied over the life of the bond, reproduces its price. And from the price, we also extract the instantaneous forward rate, F of TT. This is the rate locked in today for borrowing at the instant T. Now let us see all 3 in action. I will use a realistic yield curve to plot the bond price on top, the yield in the middle, and the forward rate at the bottom. Watch the white cursor. As it moves across maturities, you can read off all 3 values simultaneously. At short maturities, the bond price is close to 1, the yield is about 3%, and so is the forward rate. At long maturities, the bond price has dropped substantially. Both yields and forwards have risen. But notice, the forward rate sits above the yield at every point. These 3 quantities are not independent. There's a beautiful identity connecting them. The forward rate equals the yield plus the maturity times the slope of the yield curve. Think of it like the marginal cost versus average cost relationship from microeconomics. This has an immediate consequence. When the yield curve slopes upward, the forward rate sits above the yield. When it slopes downward, the forward rate sits below. Watch. As I move the cursor, the forward rate dot is always above the yield dot on our upward sloping curve. There's one more key definition. The short rate, ER of T, is the instantaneous rate at the very start of the curve, the limit of the yield as maturity approaches the current time. It is where the yield curve begins. And in the next section, we will ask a powerful question. What if, instead of observing this rate, we model it as a stochastic process? That is the Vasicek model. In 1977, Aldrich Vasicek proposed the simplest stochastic model for interest rates. The short rate follows an Ornstein-Uhlenbeck process. It is pulled toward a long-run mean B at speed A, with random Gaussian shocks of size sigma. For our demonstration, we set the mean reversion speed to 0.5, the long-run mean to 5%, and the volatility to 2%, starting from 3%. If you watched episode 1, this is the same Brownian motion, but now with a spring pulling it back toward the center. Now let us simulate 50 independent interest rate paths over 10 years. Each line is one possible future for the short rate. Notice how they all gravitate toward the 5% level, the golden dashed line. That is mean reversion in action, but look carefully. Some paths dip below 0. They are shown in red. Vasicek rates are Gaussian. Their support is all of the real line. The probability of going negative is never 0. For decades, this was considered a fatal flaw of the model. Then reality caught up with the math. In June 2014, the European Central Bank set its deposit rate below 0 for the first time. In January 2016, the Bank of Japan followed. Switzerland, Sweden, and Denmark also went negative. The model's bug became its most prescient feature. Vasicek gives us a closed-form bond price. It is affine in the short rate. Log of P is linear in R. The function B of T measures how sensitive the bond price is to the current rate. And here is a beautiful result. The long-run yield, as maturity goes to infinity, converges to B minus sigma squared over 2a squared. That is 4.92%, not 5%. The gap of 8 basis points is a convexity adjustment, a consequence of Jensen's inequality applied to the exponential discount factor. Long yields are always lower than the mean rate. Vasicek has a problem. Its volatility is constant, so rates can go negative. In 1985, Cox, Ingersoll, and Ross proposed an elegant fix. Replace the constant volatility with sigma times the square root of R. The difference is 1 square root, but the consequence is profound. When the Feller condition holds, 2ab is at least sigma squared, the rate stays strictly positive. With our parameters, 0.05 is indeed greater than 0.01. The square root term acts like a valve. As R approaches 0, the volatility shuts off, and the drift pulls it back up. Here are the two yield curves side by side, both starting from a short rate of 3%. They look remarkably similar. Both curve upward toward a long-run yield near 5%. The asymptotic yields are almost identical, 4.92 for Vasicek, 4.90 for CIR. The difference is subtle but structurally important. CIR guarantees positive rates. Vasicek does not. What Vasicek and CIR share is something deeper, a fine structure. In both models, the log of the bond price is a linear function of the short rate. Alpha and beta depend only on the time to maturity, not on R itself. This is the affine term structure classified by Duffy and Kahn in 1996. An affine structure gives us a stunning visual consequence. Watch what happens when I move a single slider, the short rate R of T. Here is the Vasicek yield curve starting at 3%. As I raise R to 6%, the entire curve shifts upward. Short maturities move the most. As I bring R down to 1%, the curve drops, but the long end barely moves. The long-run yield at 4.92% acts as an anchor. It does not depend on the current rate at all. One number, the short rate, controls every single yield on the entire curve. This is why central bankers obsess over a single policy rate. All the models so far are dynamic. They describe how rates evolve over time. Nelson-Siegel in 1987 took a completely different approach. They asked, can we fit the shape of today's yield curve with just 4 parameters? Beta 0 sets the level, the long-run yield. Beta 1 controls the slope, the difference between short and long rates. Beta 2 adds curvature, a hump at intermediate maturities. And lambda controls where that hump peaks. With our demo values, the short rate starts at 3% and the curve rises to 6% at long maturities. Here are the 3 loading functions. The level loading is simply 1, constant across all maturities. The slope loading starts at 1 and decays to 0. It affects short maturities more than long ones. The curvature loading starts at 0, rises to a hump, then falls back to 0. It only affects the middle of the curve. Now watch what each parameter does to the yield curve. Here is our baseline curve. When I raise beta 0, the entire curve shifts up uniformly. This is a level shift, back to baseline. Now I raise beta 1. The short end rises while the long end stays put. The curve flattens and eventually inverts, back to baseline. Raising beta 2 lifts the middle of the curve, creating a hump, and back. Finally, reducing lambda pushes the curvature peak out to longer maturities. This model is not just academic. The European Central Bank, the Bundesbank, the Bank of Japan, the Riksbank, the Swiss National Bank, and over a dozen central banks worldwide use Nelson-Siegel or its Svensson extension as their official yield curve fitting method. But there is one question we have not answered. How do you choose the best values of beta 0, beta 1, beta 2, and lambda to match real market data? That is the problem of calibration, and it will be the subject of episode 19. Every model we have seen so far starts with a single number, the short rate R of T, and derives the yield curve from it. Heath, Jarrow, and Morton, in their landmark 1992 paper, flipped the approach entirely. They modeled the forward rate at every maturity simultaneously. Each forward rate f of t follows its own stochastic differential equation with its own drift alpha and its own volatility sigma. But here is where episode 12 comes back. No arbitrage does not allow alpha and sigma to be chosen independently. Let me show you what this looks like. This surface is the forward rate curve evolving through time. The horizontal axis is calendar time. The depth axis is time to maturity. And the height is the forward rate. As time moves forward, the entire curve shifts and ripples, like a wave propagating through the term structure. From this angle, you can see how the initial Nelson-Siegel shape gradually changes under the Holy dynamics. And here is the most beautiful result in all of interest rate theory, the HJM drift condition. The drift alpha at maturity t equals the volatility sigma at t times the integral of sigma from t to t. In other words, specify the volatility structure and no arbitrage forces the drift completely. You do not get to choose both. Consistency does it for you. This is the same deep pattern we saw in episode 12, now elevated to an infinite dimensional setting. Different choices of the volatility function sigma give different classical models. Ho and Lee chose a constant sigma, giving Gaussian rates like Vasicek. Hull and White added mean reversion and the ability to fit the initial yield curve exactly. Brace, Guttaric, and Musiela built the market standard model for pricing caps and swaptions by working with discrete forward rates. All of them are special cases of HJM. Once you have a yield curve and forward rates, you can build derivatives on them, just as Black and Scholes built options on stock prices. A caplet pays the difference between a floating rate and a fixed strike if the floating rate exceeds the strike. It is a call option on interest rates. A floorlet is the mirror. It pays when rates fall below the strike. A put option on rates. Here are the four fundamental payoff shapes. Top left, the caplet. 0 below the strike, linear above. Exactly like a call option. Top right, the floorlet, the mirror image. Linear below, 0 above. Bottom left, a swap. A simple linear exchange. You receive floating, pay fixed. Bottom right, a swaption. An option to enter the swap. The kinked payoff of choice, and they are connected. Cap minus floor equals swap. This is put-call parity for the interest rate world. To price these derivatives, the industry uses Black's 1976 formula, the same structure as Black-Scholes, but applied to forward rates instead of stock prices. The inputs are the forward rate F, the strike K, and a volatility sigma. But which sigma? If you recall episode 15, implied volatility is not flat. It forms a smile. The Sabiar model, originally built for equities, is now the industry standard for pricing interest rate caps and swaptions. The same math applied to a different market. Before we close, let us look at a completely different world that uses the same core idea. On the left, the traditional treasury yield curve we have been studying. Rates depend on maturity. On the right, a DeFi lending protocol like Aave. Rates depend on utilization, how much of the pool is being borrowed. At 80% utilization, the rate curve kinks sharply upward, a built-in penalty to prevent the pool from running dry. Same fundamental insight. Interest rates are not one number, they are a function. But the mechanism is entirely different, market-driven versus algorithmically set. Now for the bridge between finance and machine learning. In the HJM framework, you specify the volatility function, and no arbitrage forces the drift. The constraint is an explicit, computable integral. In energy-based generative models, you specify the energy function, and consistency forces the normalization constant z. But unlike HJM, z is intractable. Both fields face the same deep pattern. Specify one ingredient, and a consistency constraint determines the rest. HJM is the lucky case. The constraint has a closed form. Energy-based models are the hard case. Machine learning develops elaborate workarounds like score matching to sidestep the intractable z entirely. In the episodes ahead, we take both paths further. Episode 18 dives deep into the mathematics of DeFi protocols, concentrated liquidity, and algorithmic rate curves. Episode 19 tackles the ultimate question. How do you calibrate all of these models to real market data? Thank you for watching. I will see you in the next one.